All right, yesterday we started looking at rules, take derivatives, and we looked at a few of these. We had our constant multiple rule, right? Which said, constant function. If you have a constant function, the derivative is 0. We proved that one. We had the power rule, which is where you brought down the exponent and subtracted 1. One of the things we'll talk about today is you'll notice this nowhere does it say anything about what n has to equal. So n can really be any number, and this still works. We'll look at some examples of that today. Yesterday we did polynomial ones. We looked at the constant multiple rule, which basically tells us if we have something like 2x cubed, we can bring down the 3 and multiply, get 6, and then subtract 1 to get our derivative. Or here, bring down the 5 is 20, subtract 1 to get our derivative. Okay? So we want to look at a few other rules or properties today. The first one is the sum or difference rule. This basically says if you have the derivative of two functions, they like to use u and v for some reason when they do this, that we can just take the derivative of u plus take the derivative of v. Or another way of thinking about it, if we actually prove it here, if I take the limit of f plus g derivative, so that's putting it in the formula, I can kind of divide this out into just the derivative of f, just the derivative of g, which then gets me my rule of two separate derivatives. Okay? Now, what does that mean? If I have something like x squared plus 1, what that means is I can take the derivative of x squared, which is, bring down the 2, that'd be 2x, plus, what's the derivative of 1? What's the derivative of a number? 0. So, or just 2x. So, what would be the derivative here? I could just take the derivative of each part. The derivative of 4x squared would be 8x. The derivative of negative 2x is just negative 2. And the derivative of 3 is 0. So you can just do each one separately as you take the derivative. Okay. All right. So, is this on? I have. I have the notes in front of me. Is this one on your notes?
Yeah.
Okay, so let's look at our derivative. So what would be the first derivative? You would bring down the 3, 6x squared. If you have a negative 2, I bring down the negative 2, and then what would my exponent be? So what do? You bring down the exponent and you subtract 1. So what is negative 2 minus 1? Negative 3. And then minus 1 goes to 0. That's the first derivative. Now, let's take the second derivative. We just do the derivative again. Bring down the 2. Bring down the negative 3, which would be plus 6x. Subtract 1 again. You get negative 4. Try doing the third derivative. The third derivative would just be 12 minus 24x to the negative 5. Okay. All right. I'm going to skip some of these next ones. We'll come back to them. So let's talk about our notation here. So another way you can write the same problem is I could say, what is d dx of 2x cubed plus x to the negative 2 minus 1. So instead of using the f prime as writing a function and its derivative, we could write it like this. This would be the exact same thing. That's just a different notation for derivative. Now, let's say we want to take the second derivative. So if I wrote this like this, d dx of d dx of 2x cubed plus x to the negative 2 minus 1. Do you see how that'd be the derivative of that? Same notation. The way we write that, though, is like this. Notice the top we have d, so we write d squared dx squared notice that d's at the top become d squared, and then the dx's at the bottom, we write it like that, dx squared. So if I wrote what is this, that would just be what? The third derivative. So you have to find the first derivative, find the second derivative, find the third derivative. So those things are basically the same thing. We can write them as f prime, f double prime, f triple prime, or we could write them as d dx, d squared, dx squared, or d cubed, dx cubed. Those basically mean the same thing as first, second derivative. Okay. The last thing I want to look at here, before we just do some practice, is let's say we have the derivative of the square root. Okay, you just saw this a second ago if you're paying attention. Okay, so how do we do that? Now, we could do our whole limit, right? I'm just going to write it out for fun. We could solve that limit. Actually, I'm pretty sure we did an example of that at some point in the last chapter, where we had to do the multiply by the conjugate to make it work out, which we could do it to prove it, but I think you just take my word for it that it works out. Okay? How we're going to deal with this is like this. Anytime we are dealing with radicals, we never want to take the derivative of a radical. What we always want to do is we want to think of this as x to the 1/2. All of our derivatives, we want to take derivatives and deal with stuff in terms of it being an exponent, not in terms of a radical. So I want to write that as 1/2. So the derivative, if it's to the 1/2, I bring down the 1/2 and I subtract 1. That is my derivative. Okay. Now, sometimes, for right now, just leave it like that. That's good. If we wanted to simplify it later, this would be 1 over 2x to the 1/2, which would be 1 over 2 square root of x if you wanted to write it again as a rectangle or as a radical. Many times it's easier to do algebra with radicals, multiplying them, adding them, doing those kind of stuff that we're used to. But when you do derivatives, everything has to be exponents to take derivatives. Okay. All right. What we want to do the rest of the time here is we just want to do some practice. We're just going to try some practice problems. So I'm going to pause it here, and then we will come back and do some practice. So as you look at these, just a few things for us to kind of understand. First off, you'll notice there's 3 different ways of writing the derivative here. If I have f of x, the derivative is f prime of x. If it's h of t, my derivative is h prime of t, right? The variables stay the same. Here, you'll know 5 over r cubed. You'll see the variable is r. So it is d dr. So your derivative has to do with what the variable is. If I had x to the pi over here, d dx would be my derivative. Here I have w is the function, t is the variable, and so I want what is dw dt is my variable. Okay? So let me give you an example. Let's look at a simple example here to help us understand this. Let's say I have what is d dx of ax plus bx squared. A and b are just numbers. What would the derivative of that be? The derivative of x would be just a. The derivative of x squared, I would bring down the 2 and subtract 1. We don't really need the 1 there, but right. Now, imagine if I did this. D dA. Now, what's my variable? A. So what is the derivative of ax if a is the variable? Just x. See how it changes based on what I have out front for what the derivative is? What would be the derivative of b to the x squared with respect to a? Is there any a's there? So it's just a constant. So what's the derivative of a constant? 0. Because that's just some number based on that. So we can have equations that have multiple variables, and then what's out front tells you, hey, which one of these variables is a variable, and then all of the others are constant. Okay, as we do these, as these get more advanced. Okay, let's try one. Flip your paper over to the back. We'll try one before we continue on. So let's say, I'm going to write it this way. Y is ax squared plus abx plus xb squared. So what is dy dx? What is dy dA? And then finally, what is dy dB? So try that. Y is ax squared plus abx plus xb squared. And then find dy dx, dy dA, and dy dB. Give you a second to try that, and then we will come back. So you see, as we look at those, you have to consider, okay, what's the real? Think of it this way, this may help. If I said x is my variable, what is the derivative of 3x? 3, just 3. So if I said my variable is a, what's the derivative of 3a? 3. So if my variable is a, what's the derivative of x squared times a? Just x squared. Because in terms of a, this is just a number in front. So that's why when I do these here, if I'm taking the derivative of xb squared with respect to x, it's just b squared. It's just a number times x. Makes sense? All right. As we look at these, I want to look at these right here. Notice 5 and 6. This is just first derivative, second derivative, third derivative. And I just want you to see here, we're not going to go through and do these necessarily, but can you see how this is if you're given a function f of x and you have first, second, third derivative. If you are given a function, you write f prime, f double prime, f triple prime. If you're given an equation y equals, then you have dy dx, d squared y dx, d cubed dx. And so your derivatives here, this would just be 6x squared plus 3x to the negative 2 plus 4. Next derivative, 12x minus 6x minus 3. And then 12x plus 18x to the negative 4. Or just 12. I think I said 12x. 6, the derivative of e to the x is just e to the x. We told you that. We still got to prove that. So the derivative of e to the x is just e to the x. So second derivative, e to the x. Third derivative, e to the x. It never changes. E to the x is your favorite function in the world as we go forward, right? It's just itself. Now we'd have minus 8x cubed minus 24x squared minus 48x. All right, let's finish up. Try the bottom one. Find the equation of the tangent line to the curve at the given point. So let's look at it. So we want to find the equation of our line is y equals m, right, x1 plus y1, right? But this m right here is just f prime of negative 1. So the whole point of what we're doing now is we don't have to do the limit definition anymore. We can just find f prime. Now, from what I said earlier, what do we do with a radical? Make it a fraction. So this is x to the 1/4, right? So that would be 1/4 x to the negative 3/4 minus 1. So let's pause there. Do we understand how we got the derivative? We bring down the 1/4, we subtract 1, which gives us negative 3/4 minus 1. Now, to find our slope, we have to figure out, okay, what is this equal to when we substitute in 16? And for right now, to make our life easy, we could just come here and say 1/4, 16 to the negative 3/4, which is 1/32. So this is 1/32. So our equation is 1/32 x minus 16 minus 14. This should be a y there. The goal at this point is you do not have to do the limit of f of x x plus h, you don't have to do all that stuff. Like I said, that will eventually be on the midterm and the final again, but for right now, we're using our rules of derivatives to find the derivative. Okay? All right, homework. We have 2 delta math. There's a part 1, and there's a part 2. They're both not super long that we can work on.